We're going to complete this lesson now. We're just going to continue where we left off. So at different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, so now they're using S of x. Don't let that confuse you with position. They're actually using S of x, represented in meters per second, to talk about the speed. And x is the altitude in kilometers. And they want to know what is the average speed over the time interval 0 to 80. So again, I'm looking at the total area under this curve, but I'm trying to find the c value that would create some f of c so that it forms a rectangle where that rectangle is equal to that actual area under the curve. Okay? So what we're going to do, now we have to actually break it up. We're going to do the integral from 0 to 11.5. And we have to go 1 over 11.5 minus 0, 1 over b minus a of my function minus 4x plus 341. Plus, now I would go 1 over b minus a, which is 22 minus 11.5, integral from 11.5 to 22 for that next time block. 295 dx, plus I'm going to do 1 over 32 minus 22, integral from 22 to 32 of 3/4 x plus 278.5 dx, plus the integral from 32 to 50 of 3 over 2x plus 254.5 dx, plus, and I missed the 1 over b minus a here, plus 1 over b minus a, 80 minus 50, integral from 50 to 80 of minus 3 over 2x plus 404.5. And then we integrate this, find the answer, which will be found under the content section with this lesson filled in properly, of f of c. And this will give me the value of f of c.
Please pardon this interruption. Mr. Little. Mr. Little, would you please call the main office? Thank you, Mr. Little.
That's f of c. We just work out those integrals. So for now, I want you to try to practice the math number 9 key to see if you can get the value of that, and you'll find it in the answers when I post the lesson. Okay. Now the second fundamental theorem of calculus talks about taking the derivative of an integral. Okay. So in this first example here, I give you a constant for a constant for b. That's like my x equals a to x equals b of some function, and I'm interested in finding the area under that curve for that function. This answer would be a number that represents the area of the curve. Now here, we're going to start looking at this integral where the lower limit is a number, but the upper limit is a function of x. And when we do that, we're sort of looking at an accumulation function, sort of like an accumulation of an area starting at x equals a to whatever point I want of the function. And it still represents area under the curve, but it kind of represents it as an accumulation function. So this answer will be a function. Okay, let's look at an example. So the definite integral is a function. So we want to evaluate this function at different time points. So what we're going to do is first find the antiderivative. The antiderivative of cosine is sine t, and remember the derivative of sine t is cosine, so I don't need a negative here. I evaluate it from 0 to x. So this would be sine of x minus sine of 0, which is just sine of x. So it's telling me that the area under the curve from 0 to some value of x is given by the sine of that value. So now I'm just going to sub in the values I'm given. F of 0 should be sine of 0, which is 0. F of pi over 6, so the area from 0 to pi over 6 of cos t dt is actually just the value of sine pi over 6. So remember your unit circle values. Sine of pi over 6 would be 1/2. F of pi over 4 would represent sine pi over 4, which is root 2 over 2. F of pi over 3 would represent sine pi over 3, which is root 3 over 2. And f of pi over 2 would represent sine pi over 2, which is 1. So it kind of shows you how the area increases. So these values are kind of getting larger all the way up to 1, which we know. And it kind of shows how that area accumulates until when you hit f of pi over 2. Okay. Now, when you look at this, it says that the derivative of f is the original integral. So if I were to take the derivative of this f function, so if I were to take f prime of x, well, we figured out f of x was sine x by doing all of that work. And then we know that the derivative of sine x is cos x. So what they're asking you to notice is if I look at this cos x, it's no different than seeing this cos with the x being subbed in from the top. Okay, now this will help us lead into the second fundamental theorem of calculus, which kind of tells us that if I want to do an integral here, if I want to do the integral of that function and then take the derivative of it, like I did down here, it's no different than just taking that inner function, cosine t, replacing it with an x, and then writing that as the value of my answer. So what the second fundamental theorem tells us is if I have a function, I have an integral that I'm interested in calculating, but I'm also doing the derivative of an integral. Okay, now to do this, again, what we're saying is that we take this f of t, we don't antiderivative it, we don't derivative it, we just literally take that function, f of f, and replace the argument of that function with the x, which is represented from here. Now what's going to happen is you're actually going to see chain rule applied to this, and you'll see that in an example. We're going to kind of omit the proof for right now, but we'll show an example of what we're doing here. Now if I ask you to integrate square root of t squared plus 1, we actually don't know how to integrate this function, nor will we learn this until Calc 2, if you end up taking Calc 2 in university. So this says that I want to find the derivative of the integral. So using the second fundamental theorem of calculus, and also just knowing that a derivative and an integral kind of cancel each other out, all I'm going to do is I'm going to take the function. I'd get x squared, so instead of using a t, I use the top value subbed in, x squared plus 1, and then that would be my final answer. This would represent doing an integral first, which is this step, getting an answer, and then actually taking the derivative of that answer. Okay. Now, these questions are really popular for AP exams. They're saying find the derivative of a function. So what I want to do is if I'm trying to find the derivative of a function and my function is an integral, okay, this will hint me to second fundamental theorem of calculus. So it's hinting you by knowing that we're doing a derivative of an integral. Okay, so the derivative f prime x of this integral d dx of this integral to x cubed cos t dt is going to actually equal me having cos, subbing in x cubed, but now because this one is slightly different and I have an x cubed, I kind of have to apply the chain rule and multiply this by 3x squared so I can balance it out. Now, if you don't believe me, what we're going to do is we're going to take f of x and we're going to actually work it out to show you. So if I manually work this out, the integral of cos t is sine t because the derivative of sine is cos. I want to evaluate that from pi over 2 to x cubed. So I sub in sine x cubed plus, minus sine pi over 2, which is the first fundamental theorem of calculus. And that's my answer. Now, if I want to do the derivative of this function, now all of a sudden, when I see this part of my function, there's chain rule when I take the derivative. And because this part is a constant, the derivative will just go to 0. d dx of that thing will just go to 0. So my derivative is, what's the derivative of sine of something? Cos of something times the derivative of the something, which is 3x squared, minus 0, and you get the same answer that we just got above here. Now the next theorem we're going to cover is sort of the net change theorem, which is super, super, super important. Okay? It tells me that if I want to do, well, the first part is that if I want to do the integral from a to b f of x dx, area under the curve, it's equal to the antiderivative function. You take the top limit, sub in the bottom limit. Okay? Now, what we're saying is this little f of x, we use that symbol to represent our function, but it's actually representative of a derivative. I have a derivative and I'm going back to the original function. So if I take this little f of x and sub it in with capital F prime of x, which is the same thing, I get the exact same result, and this will lead us to the net change theorem, which is this right here. It's saying that the integral from a to b of some derivative is the same thing as getting that function with the b value subbed in minus the a value subbed in. Now, on the AP exam, you're going to know that this is net change theorem because what they're going to say is that they're going to give you a function and it's flowing at a rate. So they're going to kind of use this word rate at you, which is telling you you're using net change theorem, okay? It's giving you like a derivative. So this is like my capital F prime at x, or in this case, t. And they're asking us to find the amount of chemical. So that's now referring back to the function without the derivative that flows into the tank during the first 20 minutes. Okay? Now, so here we're going to do the integral of 180 plus 3t dt. And we were interested in the amount of chemical that flows in the tank for the first 20 minutes. So my integral is only going to go from 0 to 20. So now, like, regardless of whether I'm using the net change theorem or not, I've given a function here. To do this integral, I take the antiderivative of the function, which is 180t plus 3 over 2t squared. And I want to evaluate that integral from 0 to 20. Okay. So I take 180 times 20 plus 3 over 2 times 20 squared minus, subbing in 0 here and here will give me a 0. So when I work that out all said and done here, when you give me a moment, you get 4,200 liters. So this kind of tells me that in the first 20 minutes, 4,200 liters of chemical was in the tank during the first 20 minutes. And this represents the rate of flow of that chemical in the tank. Okay, another way you can think of the net change theorem, it's like literally saying I give you a derivative function and you want to go back to the original, you're taking an antiderivative. So what this is saying is if I give you the velocity function and it's a derivative of position, well, if I do the integral of velocity, so the integral of velocity, as we learned earlier, gives me the position function, and now I'm just adding these limits in to find it over a specific time interval, and you'll see that I'm subbing it into my position function, which is the antiderivative of the velocity function. Okay? Now this definite integral represents the net change. So if I have positive areas, these positive areas would get added together. And then if I have a negative area, this area needs to get subtracted off. And these together would give me sort of the total displacement in the time interval. Okay? Now when I want to find the total distance traveled by the particle, total distance, I'm given a velocity function. I integrate that velocity from lower limit to upper limit or over the time interval I want. You'll notice I'm adding A1 and A3 because those are areas that are positive or sitting above the curve, and I subtract off area 2, which is below the curve. But if I was interested in finding total distance, which is something different, I need to do the absolute value of the velocity function, which means that this bottom half is sort of flipping up, and I need to add up all the areas, A1, A2, A3. So be careful when they ask you the total distance versus the net change. Anytime they use the word total, you need to remember you're having sort of an absolute value of your velocity function in there. Okay. Example 10, they're giving me a velocity function of a particle moving in a line. Here's my velocity. I know to go from position to velocity to acceleration, I take a derivative. We know that. So now we're sort of learning that when we want to go in the reverse direction, we actually just integrate that function. And then if they give us a time interval, we apply the fundamental theorem of calculus and just sub in that time interval. What is the displacement? We're talking about the net change. So we're just doing an integral. So we're doing integral on some time interval, 1 to 5, of my velocity function, which is t cubed minus 10t squared plus 29t minus 20. When you look at it like this, we're just doing an antiderivative and subbing it in. If this is my velocity function, then it literally means take my position function, sub in the top limit, minus sub in the bottom limit. So you're going to actually work this out. T to the 4 over 4 minus 10t cubed over 3 plus 29t squared over 2 minus 20t. You're going to evaluate from 1 to 5 and then work out that total final answer, which should be, let me look here, maybe 32/3, but maybe double check that. Again, I will post the full answer key for you so that the notes are filled in kind of a little bit clearly. When they're asking me to do the total distance, I need to go from the integral 1 to 5 of the absolute value of t cubed minus 10t squared plus 29t minus 20, and then dt. So now you have to be careful, because when you look at the graph of this function, which, I mean, maybe this would be a graphing calculator question, the graph looks something like this. This is 1, this is 4, and this is 5. This is my velocity function, which is given, and this is time. So I need to break up my integral from 1 to 4 of the absolute value of velocity, which in this case would just be the velocity function because it's already positive, plus the integral from 4 to 5 of the absolute value of my velocity function. Now, this case, it is important to put the absolute value in because this part is negative, but I kind of want to flip it up and think of it as a positive area. So what I could do is I could do this integral plus, I'm going to go from 4 to 5, but instead of using velocity, I'm going to use the negative of velocity, so I get the function in reverse. So negative of t cubed minus 10t squared plus 29t minus 20 dt, and then I would work that one out as well and get one final answer, which I will have in the answer key for you. Okay, I hope that makes sense to you. Please let me know if you have any questions via email, and I will put a complete solution key for this lesson up for you